Hi, welcome to another session of Circuits and Networks. In today's class 6 under GATE exam, we are going to see simple problems on network elements, that is inductors and capacitors. In our previous classes, we have seen problems related to resistors. Now we are going to see the problems related to inductors and capacitors, and that two simple problems. So we'll go with the basic problem. Energy stored in a capacitor over a cycle when excited by an AC voltage source is options given as the same as that due to a DC source of equivalent magnitude. Option B, half of that due to a DC source of equivalent magnitude. Option C, 0, and option D, none of the above. So this was a question framed in GATE 1997 for 1 mark. For this, we should know the basics of ACs, that is sine wave, cos wave, and their derivatives or integrations. Apart from that, behavior of capacitor and inductors with their initial conditions and final conditions. So for this, you can check our previous classes for capacitors and inductors, and then you can come back to this problem. So let us go with the solution. Let us assume that V of t is equal to sine omega t as supposed to be given by the problem, that is AC source, that is sine omega t. If V of t is sine omega t, then current through the capacitor is given by I of t is equal to C dV by dt. In fact, V of t is sine omega t. So differentiation of sine omega t will give us the value as C omega cos omega t. Now once we are done with V of t and I of t, let us frame these equations as 1 and 2. And let us calculate the instantaneous power, that is P of t, which is the combination of V of t and I of t. Remember, we are treating all the values as instantaneous values. Okay, when we substitute the value of P of t, I of t, we are going to get sine omega t, C omega cos omega t from equation 1 and 2. Let us take C and omega outside, then we are going to be seeing that we have framed an equation C omega sin omega t cos omega t. In fact, sin omega t cos omega t, if at all you multiply and divide this equation by 2, we'll get sine 2 omega t. In fact, divided by 2, we'll be having this value as C omega by 2. So let us multiply and divide equation 3 by 2, we get P of t is equal to C omega by 2 sine 2 omega t. Now, when we are interested to know the energy stored in the capacitor, we are going to apply limits to the power equation. So 0 to t p of t, which will be equivalent to c omega pi 2, we can take it outside. So the limits of value will be 0 to 2 pi for one cycle, sine 2 omega t dt. In fact, sine 2 omega 2, sine 2 omega t dt with the interval of 0 to 2 pi will give us the value as 0. So from the given options, C is the right answer. In the next question, in the circuit shown in figure, it is desired to have a constant DC, that is direct current I of t through the ideal inductor L. The nature of the voltage V of t must be, the options given are constant voltage, linearly increasing voltage, an ideal impulse, and exponential rising voltage. So this question was asked in GATE 1998 for 1 mark. So you know, again you should know the basics of inductors behavior with initial and final conditions, voltage formula of inductor, current formula of inductor, and then you can start with the solution. So from the solution we know that V of t is equal to L di by dt, that is the voltage across inductor given by this formula. Now when you try to obtain the value of current, you have to take the integrations on both sides. You'll get the I of t equivalent to 1 by L integration minus infinity to t V of t dt. Why we taken the value as minus infinity to t? So, such that we should know what is the previous voltage that is being applied. So previous voltage, that is why we have taken minus infinity to the required value, that is t. So that is the limits have changed from minus infinity to t. Now with these conditions, if at all we choose option C, an ideal impulse, for example, when V of t is an ideal impulse, that is the delta of t, when you're going to integrate this delta t, you're going to get I of t is equal to 1 by L, that is nothing but a constant value. And the question is given that it is desired to have a constant DC current. So if at all you do this, this value, that is impulse value delta t, by looking into the option C, you'll get an instant answer. such that integration of minus infinity to t del t dt is equal to 1 will give us a constant current which is flowing through the inductor. So this is valid for t greater than 0 from that instant of time. So v of t must be an ideal impulse. So option C would be the right answer. You can cross check by giving to looking to the other examples, that is A, B, and D, and comment in the chat box what answer you are going to get by looking into the options. So it's a 1 mark problem. So option C is the right answer. In question 3, for the circuit shown in figure 3, the capacitance measured between the terminals B and Y. So B and Y, you have the conditions. The options given are A, B, C, and D. So what we are going to do by looking into this figure 3, rearranging the given circuit in figure 3a, we observe that, see, I have taken this ground terminal and this terminal we have grounded. So in fact, CC between B and Y, it is kept as it is, whereas CC, CS, they are parallel here, and similarly CS, CC are parallel over here. So what we are going to get, the parallel combination of CC and CS, this value we are going to get value as CC plus CS, that is CC plus CS on the left hand side and right side of figure 3a. In fact, we can change figure 3a to figure 3b like this. Now you can see we have CS plus C in series with CS plus C, and that combination is in parallel with CC. So for let us calculate CS plus CC in series with CS plus CC, whose value will be equivalent to CC plus CS square by 2 times of CC plus CS. This is simply quite opposite to the resistor calculations. Resistor in parallel will be equivalent to RA by RA plus RB. Now we have capacitance, which is quite opposite to the resistor inductor concept. So you have capacitors in series formula will be equivalent to C1 C2 divided by C1 plus C2. Here we are taking C1 as CS plus CC, C2 also as CS plus CC. So this value will be giving you the final answer as CC plus CS. Now CC plus CS divided by 2 is the combination of this series, and that is arranged in parallel with CC, which is placed between B and Y. So you have this series combination parallel with CC. Again you can add up. So CBY equal to CC plus CC plus CS by 2, which will be equivalent to 3 times of CC plus CS by 2. So this answer, that is CBY, will give you the option as C. Please comment in the chat box if at all you have any doubts in this particular problem. It's a very important problem for capacitance calculations. In the fourth problem, a voltage waveform V of t is equal to 12t square is applied across 1 Henry inductor for t greater than 0 with initial current through it being 0. The current through the inductor for t greater than 0 is given by the options given as ABCDs, that is 12t, 24t, 12t cube, 4t cube, and this was asking GATE 2001 for 1 mark. Okay. So as I said, we should know the value of voltage across the inductor, that is V of t, generally given as L di by dt, and V of t is nothing but 12t square. L value is given as 1 di by dt. So if at all I integrate on the both sides of this equation with initial conditions as 0, then I would be getting the value of I of t will be equivalent to, you have this value of voltage, that is 12t square. I'm taking 12 outside. Inductor value as given as 1. So this V of t of magnitude 12 is taken outside. Inductor value is 1. Integration of 0 to t square dt plus initial current is 0. So I'm substituting the values. I'm going to get I of t equal to 12. T, t square integration is nothing but t cube by 3. So 12 t cube by 3 will give you the value as 4t cube. So option D is the right answer. So these kind of problems were asked in past GATE questions under electrical engineering. So I hope you have got some basics of concepts of inductors and capacitors and how the questions are framed on capacitors and inductors based on their past conditions. We have represented here a gate 99, a basic problem. This is a very interesting problem. That's why I have framed this as an open pick for gate class 6. I hope you like this video, share among your friends and subscribe to my channel, and please press the bell icon for the future notifications.